Atmospheric entry is the movement of an object into and through the gases of a planet's atmosphere from outer space. There are two main types of atmospheric entry: uncontrolled entry, such as in the entry of astronomical objects, space debris or bolides, and controlled entry, such as the entry of technology capable of being navigated or following a predetermined course. Atmospheric drag and aerodynamic heating can cause atmospheric breakup capable of completely disintegrating smaller objects. These forces may cause objects with lower compressive strength to explode. For Earth, atmospheric entry occurs above the Kármán line at an altitude of more than 100 km above the surface, while at Venus atmospheric entry occurs at 250 km and at Mars atmospheric entry at about 80 km. Uncontrolled objects accelerate through the atmosphere at extreme velocities under the influence of Earth's gravity. Most controlled objects enter at hypersonic speeds due to their suborbital, orbital, or unbounded trajectories. Various advanced technologies have been developed to enable atmospheric re-entry and flight at extreme velocities. An alternative low-velocity method of controlled atmospheric entry is buoyancy, which is suitable for planetary entry where thick atmospheres, strong gravity or both factors complicate high-velocity hyperbolic entry, such as the atmospheres of Venus, Titan and the gas giants. History. The concept of the ablative heat shield was described as early as 1920 by Robert Goddard. In the case of meteors, which enter the atmosphere with speeds as high as 30 miles per second, the interior of the meteors remains cold, and the erosion is due, to a large extent, to chipping or cracking of the suddenly heated surface. For this reason, if the outer surface of the apparatus were to consist of layers of a very infusible hard substance with layers of a poor heat conductor between, the surface would not be eroded to any considerable extent, especially as the velocity of the apparatus would not be nearly so great as that of the average meteor. Practical development of re-entry systems began as the range and re-entry velocity of ballistic missiles increased. For early short-range missiles, like the V-2, stabilization and aerodynamic stress were important issues, but heating was not a serious problem. Medium-range missiles like the Soviet R-5, with a 1,200 km range, required ceramic composite heat shielding on separable re-entry vehicles. In the USA, this technology was pioneered by H. Julian Allen at Ames Research Center. Terminology, definitions and jargon. Over the decades since the 1950s, a rich technical jargon has grown around the engineering of vehicles designed to enter planetary atmospheres. It is recommended that the reader review the jargon glossary before continuing with this article on atmospheric re-entry. When atmospheric entry is part of a spacecraft landing or recovery, particularly on a planetary body other than Earth, entry is part of a phase referred to as entry, descent and landing, or EDL. Blunt body entry vehicles. These four shadow graph images represent early re-entry vehicle concepts. A shadow graph is a process that makes visible the disturbances that occur in a fluid flow at high velocity, in which light passing through a flowing fluid is refracted by the density gradients in the fluid, resulting in bright and dark areas on a screen placed behind the fluid. In the United States, Julian Allen and A. J. Eggers, Jr., of the National Advisory Committee for Aeronautics made the counterintuitive discovery in 1951 that a blunt shape made the most effective heat shield. From simple engineering principles, Allen and Eggers showed that the heat load experienced by an entry vehicle was inversely proportional to the drag coefficient, i.e., the greater the drag, the less the heat load. If the re-entry vehicle is made blunt, air cannot get out of the way quickly enough, and acts as an air cushion to push the shock wave unheated shock layer forward. Since most of the hot gases are no longer in direct contact with the vehicle, the heat energy would stay in the shocked gas and simply move around the vehicle to later dissipate into the atmosphere. The Allen and Eggers discovery, though initially treated as a military secret, was eventually published in 1958. Entry vehicle shapes. There are several basic shapes used in designing entry vehicles. Sphere or spherical section. The simplest axisymmetric shape is the sphere or spherical section. This can either be a complete sphere or a spherical section forebody with a converging conical afterbody. The aerodynamics of a sphere or spherical section are easy to model analytically using Newtonian impact theory. Likewise, the spherical section's heat flux can be accurately modeled with the Fay-Riddle equation. The static stability of a spherical section is assured if the vehicle's center of mass is upstream from the center of curvature. Pure spheres have no lift. However, by flying at an angle of attack, a spherical section has modest aerodynamic lift, thus providing some cross-range capability and widening its entry corridor. In the late 1950s and early 1960s, high-speed computers were not yet available and computational fluid dynamics was still embryonic. Because the spherical section was amenable to closed-form analysis, that geometry became the default for conservative design. Consequently, manned capsules of that era were based upon the spherical section. Pure spherical entry vehicles were used in the early Soviet Vostok and Voskhod and in Soviet Mars and Venera descent vehicles. The Apollo Command Service Module used a spherical section forebody heat shield with a converging conical afterbody. It flew a lifting entry with a hypersonic trim angle of attack of -27 degrees to yield an average LD of 0.368. This angle of attack was achieved by precisely offsetting the vehicle's center of mass from its axis of symmetry. Other examples of the spherical section geometry in manned capsules are Soyuz, Zond, Gemini and Mercury. Even these small amounts of lift allow trajectories that have very significant effects on peak G-force trajectory to 4 to 5 grams, as well as greatly reducing the peak re-entry heat. Sphere cone. The sphere cone is a spherical section with a frustum or blunted cone attached. The sphere cone's dynamic stability is typically better than that of a spherical section, with a sufficiently small half angle and properly placed center of mass. A sphere cone can provide aerodynamic stability from Kepler-on entry to surface impact. The original American sphere cone aeroshell was the Mk2RV, which was developed in 1955 by the General Electric Corp. The Mk2's design was derived from blunt body theory and used a radiatively cooled thermal protection system based upon a metallic heat shield. The Mk2 had significant defects as a weapon delivery system, i.e., it loitered too long in the upper atmosphere due to its lower ballistic coefficient and also trailed a stream of vaporized metal, making it very visible to radar. These defects made the Mk2 overly susceptible to anti-ballistic missile systems. Consequently, an alternative sphere cone RV to the Mk2 was developed by General Electric. This new RV was the Mk6, which used a non-metallic ablative TPS. This new TPS was so effective as a re-entry heat shield that significantly reduced bluntness was possible. However, the Mk6 was a huge RV with an entry mass of 3,360 kilograms, a length of 3.1 meters and a half angle of 12.5 degrees. Subsequent advances in nuclear weapon and ablative TPS design allowed RVs to become significantly smaller with a further reduced bluntness ratio, compared to the Mk6. Since the 1960s, the sphere cone has become the preferred geometry for modern ICBM RVs, with typical half angles being between 10 degrees to 11 degrees. Reconnaissance satellite RVs also used a sphere cone shape and were the first American example of a non-munition entry vehicle. The sphere cone was later used for space exploration missions to other celestial bodies or for return from open space, e.g., Stardust probe. Unlike with military RVs, the advantage of the blunt body's lower TPS mass remained with space exploration entry vehicles like the Galileo probe with a half angle of 45 degrees or the Viking aeroshell with a half angle of 70 degrees. Space exploration sphere cone entry vehicles have landed on the surface or entered the atmospheres of Mars, Venus, Jupiter and Titan. Biconic. The biconic is a sphere cone with an additional frustum attached. The biconic offers a significantly improved all-D ratio. A biconic designed for Mars aerocapture typically has an L/D of approximately 1.0 compared to an L/D of 0.368 for the Apollo CM. The higher L/D makes a biconic shape better suited for transporting people to Mars due to the lower peak deceleration. Arguably, the most significant biconic ever flown was the Advanced Maneuverable Reentry Vehicle. 4 AMAVs were made by the McDonnell Douglas Corp. And represented a significant leap in RV sophistication. 3 of the AMAVs were launched by Minuteman I ICBMs on 20 December 1979, 8 October 1980 and 4 October 1981. AMAV had an entry mass of approximately 470 kilograms, a nose radius of 2.34 centimeters, a forward frustum half angle of 10.4 degrees, an interfrustum radius of 14.6 centimeters, aft frustum half angle of 6 degrees, and an axial length of 2.079 meters. No accurate diagram or picture of AMAV has ever appeared in the open literature. However, a schematic sketch of an AMAV-like vehicle along with trajectory plots showing hairpin turns has been published. AMAV's attitude was controlled through a split body flap along with 2 yaw flaps mounted on the vehicle's sides. Hydraulic actuation was used for controlling the flaps. AMAV was guided by a fully autonomous navigation system designed for evading anti-ballistic missile interception. The McDonnell Douglas DCX was essentially a scaled-up version of AMAV. AMAV and the DCX also served as the basis for an unsuccessful proposal for what eventually became the Lockheed Martin X-33. Non-axisymmetric shapes. Non-axisymmetric shapes have been used for manned entry vehicles. One example is the winged orbit vehicle that uses a delta wing for maneuvering during descent, much like a conventional glider. This approach has been used by the American Space Shuttle and the Soviet Buran. The lifting body is another entry vehicle geometry and was used with the X-23 prime vehicle. The first system was an Aerojet proposal for an inflated Sparrow Gallo wing made up from a Connell wire cloth impregnated with silicone rubber and silicon carbide dust. First was proposed in both one-man and six-man versions, used for emergency escape and re-entry of stranded space station crews, and was based on an earlier unmanned test program that resulted in a partially successful re-entry flight from space. But otherwise it appears the concept would have worked, even with the fairing dragging it. The test article flew stably on re-entry until burn through. The proposed Moose system would have used a one-man inflatable ballistic capsule as an emergency astronaut entry vehicle. This concept was carried further by the Douglas Paracone project. While these concepts were unusual, the inflated shape on re-entry was in fact axisymmetric.